So I want to show you how this series, which we know, actually we know that this series here is geometric with a ratio of, what is R? R is going to be 1/2, right? So we know that this series is convergent, and since all of the terms are positive, it has to also be absolutely convergent, right? Because if all of the terms are positive and your series is convergent, then your series is absolutely convergent. So we already know the answer. But the reason why I put this example up here is because I want to show you how this series is perfect for the ratio test. This series is perfect for the root test. And in fact, the proofs of the ratio test and the root test rely on modeling a series after a geometric series. Okay, so first let's look at how we would use the ratio test to prove that this series is absolutely convergent. So our a sub n, our terms are 1 over 2 to the n. So that means a sub n plus 1 is going to be 1 over 2 to the n plus 1. And now L, which is the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, is going to be the limit as n goes to infinity of, now a sub n plus 1 is 1 over 2 to the n plus 1, and a sub n is 1 over 2 to the n. Okay? And so now we're going to take the limit as n goes to infinity of, and if we just rewrite this ratio, we'll have 2 to the n over 2 to the n plus 1, absolute value. We really don't need the absolute values because our terms are positive. So let's go back and erase here. Okay, and then when we terms out to the n 2 to the 1, we're just going to be left with 1/2. Right, so this is the limit as n goes to infinity of 1/2, and what is that limit? Is equal to 1/2. So L is equal to 1/2. Thank you. L is equal to 1/2. So our series is absolutely convergent, right? Because our convergent if. So for the root test, we have a different definition for L. L is equal to the limit as n goes to infinity of the nth root of the absolute value of your term. And then if L is less than 1, then your series is absolutely convergent. And if L is greater than 1, then your series is divergent. And if L is equal to 1, you have to try another test. Try something else. Okay, so for our series that we're working with, which is our geometric series, we've got 1 over 2 to the n. A sub n, what is L going to be? L is going to equal the limit as n goes to infinity. The absolute value of a sub n, what is a sub n? 1 over 2 to the n. And so the absolute value of a sub n to the power of 1 over n. Now, let's rewrap this, or unwrap it. Because what is 1 over 2 to the n? All that means is 1 over 2 to the nth power, right? So we take the absolute value of that and the nth root of 1/2 to the nth power. Those exponents are going to cancel each other out, right? N and 1 over n are going to cancel each other out. So we're going to be left with just 1/2. Absolute value of 1/2. We get exactly the same L. Right? So L is equal to 1/2. Since L is equal to 1/2, we're in a situation where our series is absolutely convergent. So these calculations over here were so neat and easy. They weren't messy. And that's because, again, the proof of the root test and the proof of the ratio test are both, those proofs are both based on taking a series and kind of pretending that it's close to a geometric series. So anytime you use the ratio or the root test on a geometric series, all of your calculations are going to be very easy and very clean. All right.